find our critical numbers, we need to identify the points at which the derivative equals 0 and where the derivative does not exist. So first up, find the derivative of our equation. And you'll notice that in my derivative here, I do have an x to a negative power, which means that that x is in the denominator of a fraction. That is, it's actually representing 1 over the cube root of x. And so we can already know then that the derivative would not exist if x equals 0. So that's our first critical number. But that's going to be the only one that comes from the derivative not existing. I still need to look for any times when my derivative is going to equal 0. And again, there's multiple different techniques that you might use to do it. But for me, I'm going to add this term to both sides. And you can work with it with the fractional exponents in there. Or if it makes it a little bit easier on you, go ahead and rewrite them in simplified radical form. So like get rid of the negative exponent and turn the fractional exponents into radicals. I find this simplified form simpler because it does bring back that idea of cross multiplying as a way to be able to go ahead and solve it from here. So I'm going to go ahead and do that. I'm going to cross multiply those through. And of course the 2 times 3, that gives me 6. And then equals the 3 times the 10 here is 30. But then we have the cube root of x times the cube root of x squared. Well, if we're going to do that, that's really like x to the 1/3 times x to the 2/3. Remember, that's where we get those cube roots from. Well, if I'm multiplying the x's, I'm adding their exponents. And so that would end up equaling x to the 3/3. And of course, 3/3 is just 1. So that would all just equal x. So much simpler. All right, so the last thing we need to do in order to figure out what x is just divide both sides by 30. 6 divided by 30 is actually 0.2. And so then that is our other critical number. So we have x is going to equal both 0 and 0.2. And once again, in order to kind of give some context to the problem, let's take a look at that graph and see what that actually means for what's happening graphically in this case. So here you can see what's going on there. And you can see, first of all, why at 0 the derivative did not exist. Because it was a corner on the graph. Hence, it was not differentiable. And then we can also see here what's going on at 0.2, where the derivative equaled 0. And that actually is a local minimum there. And you can see here at 0, that is a local maximum.